Yeah, I'm kind of out of my league. I said that and they came back.
Oh yeah. All part of the civil project. Basically, we're just putting together. I don't know exactly what we're doing. We're going to be putting together, but one of them is like. Or we can maybe rope you guys in.
All right, good morning. All right, good morning. Great to be here. My name is Dong Chen. I also go by Tony. I'm an assistant research professor from the University of Maryland.
Hi, my name is Rebecca Jordan. I'm a PhD student at FU Amsterdam.
All right, it's really great for us to be able to co-chair this session. So everyone has 5 minutes time for the presentation and 2 minutes for Q&A. Rebecca, you're gonna time them, and we'll give you, you know, a
I can do like a 4-minute note and then a 2 minute or 1 minute note.
All right. But yeah, let's get it started. So the first talk is from Thomas. Influence of snow melt timing on Arctic boreal fire season start across North America. Yeah.
Yeah, thank you. I'm indeed Thomas Hessing. I'm a PhD student from Sande, so all the way from Amsterdam. Yeah, so we've been looking a bit into the snowmelt timing in the Arctic boreal forest. And let's just have a background. This Foreman and colleague paper from 2018 looked at the spring snow cover trend over the last decades. And what they found was that it decreased. There was a decrease in the spring snow cover trend in the western part of North America, and sort of a status quo and a slight increase in some places in the middle and eastern part of North America. And we know that that may have large influence on like energy fluxes, surface energy fluxes, but also hydrology. And from our last work, we actually saw that this lightning ignition efficiency is really driven by the dryness of fuel. So we started wondering if there is like any sort of relationship between snowmelt timing and the number of ignitions and the ignition timing in this contemporary time. So what we did was we used snowmelt data from MODIS here from 2001 to 19, actually to 21, I updated, and then also we used the National Snow and Ice Data Center data as well on snowmelt. And then we combined it with burn area from Brendan's group. I think it's developed by Stefano. And we retrieve these ignitions on a daily basis using Landsat and MODIS data. And to go back in time, we then use some of the fire databases that I think a lot of us are familiar with the Alaskan and Canadian fire databases. So what we did was expanding in a bit more than the above domain. And I think to take it through, if we start with the Alaskan boreal interior up here in the corner, we see the snowmelt timing as the day of the year from all the way back to 1967 and until now, contemporary time. And what we found out was indeed the same thing as the Foreman paper, a slightly decrease, earlier snowmelt in the western part, and to some degree status quo in the central part, and especially in the southern part, an increase in this snowmelt timing. And what we then wanted to do was to relate it to the, now we see the number of ignitions. Again, if we take the boreal interior of Alaska, we see the number of ignitions throughout the time. And we see that there is generally a trend of increase in the number of ignitions. In the south, it seems to be, especially in the southeast, a bit less pronounced. And the key point for us was then to sort of link this snowmelt timing, so the day of the snowmelt timing with the day of ignition, to see if there was some sort of relationship between, an earlier snowmelt and earlier ignition. And we did that for the Modus era. And again, I would say the Alaskan Boreal interior, now that we are here anyways, we see, especially in that one, a significant increase in the snowmelt timing driving this earlier ignition. And we see that for 10 of these 16 ecoregions. And some of them are then decreasing as well, but we would have to sort of tweak some of the parameters potentially. And the next step for us will then be to sort of look at how does this early snowmelt timing influence drivers that are well known to actually drive these ignitions, such as the vapor pressure deficit, but also the fuel moisture. And I would just say thank you for listening, and thanks to the Dutch Research Council for also funding this project.
Any question? I have a question. How do you determine the snowmelt date?
We used satellite images from back in the days. We used the satellite images from the National Snow and Ice Data Center. But in the Modus era, we used the 15% fraction snow cover per pixel. That was sort of the threshold. So if it went below the 15%, we used NDSI. And if that went below 15%, we then said that was a snow melt.
So the first day that snow cover. Okay, got it. And also, technically, I think this can also apply to snow on the start of the snow on season, right?
Yeah, I have data on it, but I haven't really started analyzing it. I think we want to keep that separate, but I have also thought about looking at whether or not the fire season will actually expand or prolong.
One question, I was really interested to see that there seems to be certain areas where there's like huge variability happening, whereas other areas there is still that really tight connection. What do you think is happening in those areas with huge variability?
I think because something I left out, but we haven't really started to distinguish between the ignition cause. So some of it is definitely also due to human impact. We could set a threshold for those things, saying like, okay, before day X, we discard it as being potential human influence. While, especially in the more northern parts where there's less populated, there's less of a scatter. So that's would be what comes to mind first.
So this is ignitions. Are the ignitions tied to acreage later on in the year? Like, is that something that are the ignitions tied to final fire acreage, like at the end of the year? Could that be something that could be looked at in the future?
Yeah, I guess. I don't know. I guess it could. Yeah.
Yeah, that's really neat. I was just curious if fire seasons, like the acreage burned, also correlates to snow off in addition to ignitions. People look at.
Yeah, we have to burn the area product, so we could also do that. Yeah.
Cool, thanks.
Next up, we have presentation from Laura. Human and animal movements combined with snow to increase motor vehicle collisions in winter.
Great, hello. So I'm presenting this on behalf of my postdoc, Callum Cunningham, who led this analysis. And this is part of the Snowscapes project led by Natalie Bowman. Wildlife vehicle collisions are a pretty major problem. So in the US, they lead to more than 400 human deaths per year and over 10 billion in costs. In the above domain, collisions with moose are most common, whereas in the lower 48, collisions with deer are most common. And there's some indications that these collisions increase during the winter months. Certainly this past winter, heard a lot of accounts of moose hanging out on the roads because of the really deep snow conditions. So we had a few hypotheses about how snow and winter processes could affect collision rates with moose. The first is that the moose will migrate in the fall. And so we hypothesized that the snow could be a trigger for the migration, bringing them close in areas closer to roads. Second could be this like plowed road effect, that it's easier for them to travel on roads, and so they kind of hang out in roadways once the snow gets deep in the winter. And the third is a human behavior that it could be a lot harder for drivers to avoid, to detect moose during the winter. It's a lot darker, and then the driving conditions are more challenging with snow and ice on the roads. To look at the role of these different factors that could affect collision rates, Glenn Liston, who's a co-author on this paper, he's the developer of Snow Model. This is a physical snowpack model. And so he did a snow model run for the entire above domain from 1980 to 2020 at a daily time step. This produced 16 different snow properties and at 3 kilometer resolution. So if any of you are interested in this data set for any of your research needs, come find me. So we compiled data sets from collaborators and 113 GPS collared moose from 5 different populations in British Columbia and Alaska to look at their movements in relation to snow, and also compiled data sets of moose vehicle collisions in Alaska and British Columbia, as well as traffic from traffic stations in Alaska. So first we found that moose avoided deep snow in winter, looking across the 5 different GPS collared populations. The preference peaked at about 45 centimeters, and they barely used any areas where the snow was deeper than a meter, and that kind of aligns with their biology. We've also found this with Dall sheep in a phase 1 project, a very similar selection for snow depth at about half of chest height. We also found that in most of the populations, they moved closer to roads in winter. So most of these populations, they migrated downward in elevation in the fall once the snow started accumulating. There was one site that was completely flat, so they had nowhere to migrate downhill to. So that did lead moose closer to roads, and road use, even in the flat site, was up to 10 times higher in the winter for the moose. And this is probably, at this site, represents that plowed road effect rather than just a migratory effect. We also did find an effect of kind of human driving. So the changes in daylight hours caused a major increase in traffic volume at night. So in the winter here, the highest traffic volume is after dark, in the darkness, and we see that's when the collisions peak. So these kind of combine to cause these cyclical, this is Alaska and British Columbia, cyclical patterns of moose vehicle collisions that peak in winter And we found that they peaked in areas where the snowpack was less than a meter deep, so a little different than what you might expect, where we expected areas with deeper snow would have higher collisions, but I think because moose are moving out of those areas, that you end up having higher collision where the snow is depth is actually shallower. But during these extreme years, like we had this past winter, that result might not apply if the moose can't move to shallower snowpack. Okay, so to conclude, we found snowfall triggered a downward migration in the fall that led moose closer to the roadways at a time of year when nighttime traffic was highest. And so these modeled snow properties might be useful in predicting where and when collisions with moose are most likely. And seasonal mitigation measures like reducing speed limits at night could be useful in mitigating that risk.
Thank you so much. Any questions?
Nancy?
Oh, me? Yeah, great talk, Laura. That was really, really cool stuff. I was just curious, like in your last conclusion there, and yeah, have you talked with any sort of stakeholders or local jurisdictions about like what to do with this info and how to educate people so that we can reduce the accidents?
Well, one of our co-authors, Leonard, I don't know how to pronounce his last name, but he works for the BC British Department of Transportation, and they have a lot of outreach programs. Actually, probably tomorrow, wear a t-shirt he sent me from one of their outreach programs. And so they could definitely incorporate this kind of information in their programs. Yeah.
Cool.
So my question has to do with the modeled snow properties. So depth is one of them. What is the other properties that are modeled?
There was density, I think, SWE, and then snow on, snow off date, snow accumulation, rain on snow. Yeah, I have
Quite
to
a
look
few
at the
things.
list.
And this is
Yeah.
for all of the above
The
domain?
entire above domain.
Great.
You'll be speaking about that soon.
Yeah, so it was surprising to me that there's more traffic at night. So did you define night by the daylight, how much daylight, or do you determine
Yes.
by, 7 o'clock?
Sunset,
Yeah,
no,
okay.
sunset. And so the traffic volumes are set by the clock. And mainly driven by like the Anchorage region and Fairbanks region. And so it's commuters mainly, but it does increase in the summer. Overall traffic volume is higher in the summer, probably with a lot of tourism. But so in the winter, there's overall less traffic volume, but a much higher proportion of that, it's mainly happening after in the dark. So you end up with an increase in nighttime traffic volume, even though overall traffic volume is lower.
Yeah.
All right.
I can take a look at it. Yeah.
Yeah, we're just checking the chat because we can't see the chat from here, so
Yeah.
we don't see if there's any online questions.
Or if anyone's in this breakout room on the laptop, you can let us know. Or I can do it myself. Is there any chat? Maybe there are questions.
I can, you don't need to do it yourself. I'll do
Okay,
it.
thank you.
Okay, thank you.
All right, so next up we have Todd. Relationship between snow conditions and wildlife survey success.
All right.
Go ahead.
Thank you. Hi, everybody. Thanks for having me here today. It was good to follow Laura. Same kind of theme here. I'm going to give you an update on some research we're doing on Natalie Bowman's snowscape project. Co-authors are Kaylin Seaton, Adele Ranking, Glenn Liston, and Natalie. And then we got close collaboration with the Alaska Department of Fish and Game on this one. First two talks already set the stage for this. Snow conditions are changing, right? They're more erratic, more unpredictable. In general, the theme is with warmer conditions, snow is coming later and leaving earlier in the Arctic boreal region. And this, of course, has impacts on wildlife. And this has been studied. It's changing movement patterns, distribution of wildlife species in certain extreme events that can cause large mortalities. And that's being studied quite a bit. What is receiving less attention is the impact of these changing snow conditions on wildlife managers, on our ability to monitor and understand changes in wildlife populations, okay? So this is something that we address through this project, and specifically, we're sticking with moose here. We explored moose survey challenges. So in Alaska and a lot of boreal region, they'll do moose aerial surveys after the hunting season. The hunting season is in September. So after that, as soon as they get adequate snow cover, they'll jump in their airplanes and they'll fly several different locations in Alaska and Canada and try to estimate density. And this is really important because it helps them set harvest regulations. It helps them do all sorts of things to manage that population effectively. And they need this snow cover because it helps them see moose. You're flying over an area and it's all brush and brown. Moose are brown and they're hard to see, okay? Your detection drops so low that you can't estimate abundance with confidence. So you need adequate snow cover, and then it also needs to come before mid-December. And the reason also relates to what Laura just talked about. We lose our daylight up here. Fairbanks, we're down to around 4 hours of possible daylight by the middle of December. So the aircrafts need time to get out there and fly around. The other problem you run into why you need to do these in the fall instead of the spring, why not March? You got great snow cover, you got light coming back, right? Well, moose lose their antlers in January. So sex composition, the number of males and females, is also really important for harvest regs. So we need to get in there before these guys drop their antlers. Got it? So there's consequences of failed moose surveys. We get poor population estimates, which translates into difficulty setting harvest regs. And then there's either a loss in hunting opportunity or we screw something up and we overharvest. All right. So the objectives was to compile a bunch of data sets on annual fall moose surveys, whether they were successful or not over 33 years. At the same time, we modeled snow conditions using the snow model that Laura just talked about. And then we looked at the association between those two. What are these different snow properties that can help us understand when a successful moose survey will occur? And then the idea is after we know which variables drive a successful moose survey, we can look at how snow might be changing over the next 30 years and come up with a probability of moose survey success for our managers moving forward. So we're doing this, these little circles you see here are game management units. It's how moose are managed and how populations are estimated within these areas in Alaska. So we're looking at 6 different game management units, and our survey data sets, that 33-year data sets, tells us if they were successful or unsuccessful. Then we use this snow model output to find out what snow variables might be explaining whether they were successful or not. And then we create these statistical models of those relationships. We've done this for 2 game management units, so we got 4 remaining. But the anticipated deliverables is we're gonna come up, like right now, the managers look out and they say, is there enough snow or not enough snow? So it's really qualitative. So we're creating really a good quantitative estimate of what snow conditions are required for successful moose surveys. We're going to turn this into a model. And then the idea is to create this kind of statewide surface of how snow conditions are changing, how it's affecting probability of moose surveys, and how it might be affecting this popular method of monitoring moose moving forward. With the idea, the implications of all this is it'll help managers do their own assessments. Should we keep using this technique, or is it time to get creative and think about different ways to monitor our moose in the Arctic boreal region? With the whole idea at the end of the day, we give them this information and they can manage moose and moose hunting opportunities more effectively. Thanks.
Could you distinguish between the success of the surveys and whether or not the citability was actually good? I know that Kalen did something about 2008 where they were looking at citability and follow up to see if people were catching and actually seeing the moose in the survey planes.
That's right. So actually 2 decades ago, they put a lot of effort into detection, and how they do that is they have collared moose in the area, right? And then so they'll go out and survey that zone, and whether or not they actually found that collared moose would help them quantify detection. So they have a known, they know based on collar information that moose is there. And then based on the aerial survey, they could figure out if they saw it or not, and they could develop a detection probability. And then they also came up with kind of coarse categorical, I don't know what you'd call them, but they would go out and say whether snow conditions were poor, average, or good, but not in a real quantitative way. Like they didn't get it down to an actual estimate of cover. And so we're trying to kind of take it to that next level.
I think there's a question.
No, that's me. I
Okay.
just told people that.
Okay, just checking.
Yes.
Yeah, follow.
Just a quick follow-up, and have they kind of redone the siteability quantifications as snow conditions change to see if that's changed over time?
Not to my knowledge. To my knowledge, this will be one of the first real good explorations of that. And it has to do with the snow model output, providing a really accurate indicator of snow model properties at a good resolution that we can look at it at a small scale.
I go to Jim.
Jim,
Yeah, I was just gonna say, you could add one more bullet point to the consequences of not getting a good news survey, and that's economics. Because if you have planes poised to go out and fly, and do a survey, and then snow conditions are bad, agency loses lots of money, and that's of course opportunity cost for doing other wildlife work. And so there's also large economic incentive to get it right.
that's a good point. Not just state, federal
Yeah.
folks as well, right?
Yeah, anybody who does
Yeah,
this.
yeah. Thanks.
Although, Jim, I got part of my PhD work funded because a new survey doesn't happen 1 year. So they had to like redistribute the end of year funds.
Can I just ask a quick question?
Oh,
So this may sound stupid. Is it possible to do like night vision, like a survey, like infrared kind of thing?
Well, several folks have tried that, including myself,
Didn't work?
and those booths are so well insulated.
Okay.
It can be difficult to
Wow,
detect it.
okay, that's interesting.
There is conditions where they will jump out, but we've also tried it in the spring, and they'll seek cool areas, and sometimes you're getting false positive with rocks and all
Wow.
sorts of things,
I
but
know that.
it hasn't worked.
Also, a quick comment. I think the snow dynamics, even though I know it's not the purpose of your work, I mean, the snow dynamic product, it's gonna be extremely helpful for other type of work, like disturbance, hydrology and vegetation structure. So it would be great to be able to, access data.
Totally agree that the folks who work with ADF and GR are excited about what they're doing, but in some cases, they're more excited about how they'll apply the model. and
Yeah,
other things.
that's right. Well, we'll find you.
All right.
Yeah. All right. So next up we have Heather. All right. It's called Forecasting Climate Impacts on Hazardous Snow and Weather Related Travel Conditions for All Season Roads in Arctic Boreal Regions. Go ahead, Heather.
Thanks, yeah, so it's good that we all went in a row because I am a third person working on Natalie's snowscapes project and working with snow model outputs, so you already know all about that. So yeah, this talk, I'm talking about all season roads in this talk, which are roads like the Dalton Highway and the Dempster Highway in the Yukon, roads that are maintained year-round and that provide connectivity between the main road system and these very remote regions in the Arctic and Boreal. And obviously, many of you know, traveling on these roads, especially in the fall through spring time period, the safety of travel and the ability to travel at all depends a lot on snow and weather conditions. And since we know that snow and weather are being altered by climate change, we were interested in quantifying the effect of those changes on future trends in the frequency of hazardous road conditions on these roads, which of course is important for anyone who travels on the roads and also for people who are tasked with planning for budgeting and maintenance on these roads. So to do this, we got some past travel conditions. So 511 road condition reports that you get like from the DOT, for example. We got about 10 years worth of data for both the Dalton Highway and for the Dempster Highway, or at least the portion of the Dempster within the Yukon. And we paired those with past snow and weather data, which we got from Snow Model, which you've heard about. So with that, we have daily snow and weather output. And by pairing that with the 511 conditions, we could build models to predict road conditions, travel conditions based on snow model output. And so these are travel conditions like wet and icy roads, blowing and drifting snow, that sort of thing. And then to go into the future, we could use GCM future climate simulations. We used RCP 8.5 and use those simulations to drive snow model. Then we can get daily future snow and weather conditions, which we could feed into the random forest models we've built and use that to predict future travel conditions on a daily basis. And in this talk, I'm just going to give a few results from just the Dalton Highway. So yeah, so here's for 3 different conditions, all relating to wet and icy roads. And these figures, you can see the x-axis is just month, running fall through spring, September through May. And on the y-axis is the fraction of days per month that we are predicting with our models that these conditions will occur. And the different lines in the figures are different time periods going to the future. So starting with the last 15 years and then going through 2100, the distance that the GCM ran. And this is for the, this is the GFDL CM3 RCP 8.5 model driving snow model to get these results. And a lot of the results are kind of what you would expect, looking at that figure on the left, the icy road surface. As you might expect, the season during which we expect the roads to be ice covered is expected to decrease, expected to kind of shrink in the future, with the biggest change happening in October, really decreasing in frequency then. And going along with that, we expect to see an increase in the frequency of the roads being wet, with the biggest change again in October and also in the early spring. And you can see even creeping back toward winter. So in November and February, used to be no days expected to have a wet road surface on the Dalton Highway, but the frequency of that is expected to potentially increase over time. And then that condition on the right, the wet and icy, that's meaning simultaneously wet and icy. So that really nasty, slippery road condition you get from like an ice covered road that's starting to melt or that's getting rained on. And sort of similar to the wet road condition, we expect that to increase in frequency. But sort of reaching back to Laura's talk about the moose on the roads, we're expecting this to increase even in this sort of core winter period of November through January, when it's very dark on these high latitude roads. And so that may be especially dangerous, that we potentially have an increase in the frequency of this very slick condition during a time period when drivers may not be able to identify, to be able to see that that condition is happening. And then we also looked at storms. And in this case, for storms, I'm just talking about days when we're predicting that blowing and drifting snow would occur. And overall, so the figure on the left is showing the frequency of blowing and drifting snow on the Dalton Highway. And for the Dalton in particular, it's looking like there's going to be fewer days overall, a decreasing frequency of these stormy blowing and drifting snow days as we go into the future. But the figures on the right show that on those days, we're expecting to see potentially over time an increase in the total storm snowfall and the mean storm wind speeds for those days. So potentially fewer stormy days overall, but when they do occur, they may be more intense and more hazardous on the roads. And that's all I put into this little talk. So thank you.
You mentioned you used Merit 2 data for the past climate, which I think is like half degree or around there. Have you considered using like ERA 5 land, which is 9 kilometers? Maybe because the GCMs are such coarse resolution, it doesn't matter though.
Yeah, that we were using Merit 2 partly because it's a NASA product and because
Fair.
and because Glenn Liston, who is the snow model guru, he's used it before and had really good results with it. Okay. And snow model, Glenn's got all of this figured out for feeding this all into snow model and modules of snow model, you know, deal with the coarse resolution.
Okay.
Yeah.
Makes sense. Thanks.
No question?
It was actually what I wanted to ask Todd too, but how close to real time can you do the snow model results? If managers are gonna use it for new surveys or for this, can you get it right up to?
Be a good question for Glenn. I mean, it would depend, I think, on how big an area you wanted to run and what, you know, what resolution you wanted to run it at. it doesn't take a very long time to run the model, so I would think you could get it pretty recent, pretty up to date with the, whatever, Meritu is most recent. So I'm not sure what the timing on Meritu is, how frequently they update.
All right, thanks so much. All right, next up, we have Nancy. Mapping seasonal and decadal changes in critical wetland habitat for waterfowl in the above study domain to demonstrate advances in waterfowl habitat suitability modeling.
Hi, I'll be talking today about our wetland project, wetland for waterfowl, we call it for short, which has been focusing on developing products for improving modeling of wetland habitat in the Northwest Territories and Northern Alberta. My collaborators are Kevin Smith, who's here at the meeting, so you can ask him questions about parts of this. Bruce Chapman at JPL, and folks at my office, including Mike Battaglia, Laura Borger Chavez, and people at Ducks Unlimited Canada. And they've all been very helpful, great team. We're looking at an area in Northwest Territories, Northern Alberta, where wetlands are significant for duck habitat, the Slave River Delta and the Peace Athabasca Delta. We've developed two products, wetland type map using hybrid Landsat synthetic aperture radar methodology for two time frames to assess decadal scale changes. And then inundation used to consider within season and interannual differences in hydro period. So how inundated it is very important when it comes to waterfowl habitat. And then field validation points were used for the development of the type map shown here. So first I'll go over the two products that we co-developed with Ducks Unlimited. They've been working for a long time with this type of data, and we were helping to refine their methods. And in particular, and I showed this at ASTM 7, that's why I have this slide, so I'm not going to spend time on it. But using this hybrid approach using SAR allows you to discriminate wetland types much more efficiently and more clearly and better. So that was presented last year. I'm going to spend a little more time talking about the inundation product because that's relatively new. We've gotten to the point where we have products that will be working on validation. So these are not yet fully validated, but the process is in place. Sentinel-1 is a C-band SAR. We've collected data using data within Google Earth Engine from 2017 through 2020, 8 images each year, put it into this flow diagram where you calculate a VVHH ratio for flooded vegetation and then cross-pole intensity, thresholding and clustering, and then exporting into a place where we're able to put the classified maps, the vegetation maps into the process. What we come up with are combined single date products that show relative hydro period for a season. So this is 2017. So the numbers mean how many times it was inundated, the blue being always inundated and red being never inundated. So you can see how it changes over time, 2018, 2019, and then in 2020 was a very wet year overall, so much more area of inundation, which is really important when you think about habitat. And so we worked with our partners that are experts in looking at duck habitat modeling. How can they use this type of data in their modeling activities? They use the waterfowl breeding bird population data that is usually collected each year. The last 2 years it has not been collected, unfortunately. It's done by the US Fish and Wildlife Service. Looking at divers and dabblers, two different guilds of waterfowl. and then the land cover data and the pond counts and the inundation data. So basically, if you look at these segments, the area was, the population data was divided into segments with different buffer sizes, because that's how you can decide whether or not the landscape is 1 minute. Okay, so but for each segment, then we can look at how much open water, how much inundated vegetation, etc. Looking at understanding habitat classification and whether or not the buffer size was part of the variable. Also looking at time invariant modeling to determine baseline habitat, and then understanding the inundation product, which was the primary reason. The results were that we found there little variation related to the buffer size, but that the time invariant data appreciably adds to the diver model, and that the time-specific open water leads to improvements in the Dablet model. And I have the results of that in another talk. So these results indicate that inundation data can improve waterfowl abundance. Since I have less time than I wanted, I'm going to go on and just show some of the other things we're working on. We're exploring both L-band and X-band data in addition to the C-band, and how we can use that to improve on, in particular, our inundation mapping in collaboration with Bruce Chapman at JPL. So Bruce has put together these data. On the right-hand side is the wetland map that we've created, and these are 2 examples of times with different inundation status. The colors indicate the backscatter characteristics, which are indicating different inundation levels, or the green being uplands and the surface water, open water, being blue. These types of, you might call them fingerprints of different types, are able to be brought out, and you can see that different habitat, different types show different backscatter characteristics, which is interesting, and really part of what we're trying to build in building capability for distinguishing different inundation status. And Bruce put this in its example of the simulated NISAR data that is being developed. I think it was mentioned, someone mentioned that these data sets are available for any of the data that was collected with the airborne UAV SAR. L-band on the top is the basic data, and the 2 bottom images are the 2 simulations of NISAR that you can get from that. And finally, we have been given extra funding on top of our project to look at X-band data, and we are just starting to explore that. This is a really cool image that shows X-band, C-band, and L-band in the 3 different RGB colors, showing that we do get different phenomenology from different wavelengths as expected. And you can talk to me or Kevin about any of this.
One question. All right, let's move on. Thank you, Nancy. Next up, we have Brendan. Escalating carbon emission from North American border forest wildfires and the climate mitigation potential for fire management.
Cool, thanks. Hi, everyone. Yeah, so this was really fun work to be a part of. Was led by Carly Phillips, who's a former postdoc in our group. And I want to have a special thanks to both Randy and Allison for helping with a number of different things, getting access to cost data. I think Randy sent this photograph, and is currently drafting a resource brief. So this work came out 2 weeks ago about in Science Advances. And it's actually gotten a good bit of press, so we're hoping we can turn it into some sort of change in terms of what happens to fire management resources. So the basic motivation is that, fire regimes have been intensifying across Canada and Alaska. On the left here, you can see a graph of The observations accounting for some missing fire records in different decades, we see a pretty significant uptick, and a lot of times it's driven by the low fire years actually becoming not so low over time. And then when we look at the emissions coming from these fires, actually in the context of the continental US, they're actually about even to the rest of the US, although they're much more episodic. And to put this partly in context, there's federal fire management resources, only about 4% of those go to Alaska. And so there's a bit of a discrepancy, although of course realizing there's a lot of different considerations for fire management. So we wanted to look at, there have been a couple studies looking at like how changes in fire regimes could affect costs of fire suppression costs, fire management costs. We wanted to kind of flip that and ask the question, could we use fire management to actually influence fire regimes? And would that be a cost-effective way of keeping carbon in the ground? So the first thing that we did was a meta-analysis of how we expect fire regimes to change in the future. And so we divided our period up into historical, more or less pre-significant impacts of climate change, modern, so the last 20 years when we have really good data from both Landsat and MODIS, and then the future. And we're looking out to 2050 here, so sort of in the context of mid-century deep decarbonization, working towards net zero emissions. And what you see on the left from that meta-analysis is a sort of widening band of the gross emissions from wildfires. And then here are the net emissions. And so what we essentially did is looked at not only the emissions themselves, but regrowth from forest regrowth trajectories. And so in some years you can see it's negative, right? Because in those years, we sort of spin the simulation up for a couple thousand years to be at equilibrium. And then in these low fire years, you're getting more uptake from regrowing forests than you are getting from emissions. But when we go into the future, we see net emissions are essentially always forecast to be positive. And to put these numbers in context, I think the sort of Alaska statewide fossil fuel emissions are around 50 megatons, so maybe around here. Both California and Canada are probably somewhere up here. So the net emissions from these fires are sort of expected to be on par with some of the sort of major economies in a sense. California, if it were its own country, would be something like the 5th biggest economy. So then turning to fire management and how it influences burn area, we looked at individual fire sizes. And so for those of you who are not familiar with fire management zones, our domain was interior boreal Alaska, where most of the fires are. And it's divided up into these 4 zones, going from critical, where essentially all fires are suppressed, out to limited, where they're monitored, but not much is done. And then full and modified are somewhere in the middle. And here is just looking at a log plot of the fire sizes by those management zones. You can see obviously that the fires are a lot smaller and critical compared to limited. Again, there's a lot of factors involved. So we wanted to look at it in a little more detail. So we ran a random forest model with all sorts of drivers of fire regimes. So, mean climate, fire weather, indicators of vegetation, and still fire management zone popped out to be pretty important. And then here's the sort of influence of fire management zone on fires after all those physical characteristics are taken into account. What we did, what I think was really, really interesting on top of that, was to get cost data. So this is where the help from Mandy and Allison really came in. We wound up getting really good data from Ken Slaughter, the BLM. And we had about 1,000 fires, which we had individual costs for. And so we used, this is sort of outside my expertise, but an econometrics technique called instrument variables approach to account for the influence of all these things I just mentioned, including fire management zone. Then how much does increased spending on a given fire decrease fire size? So using that relationship and then coupling that to the carbon emissions, we can get a cost per ton of CO2, and that's what's shown here. So it's kind of a wide range, but the mean cost per ton, and essentially this is how much it costs to keep carbon in the ground, so CO2 out of the atmosphere, was about $12.50 per ton of CO2. And if you compare this to other mitigation technologies that are out there, it's actually somewhat cost effective. Some of these have very wide ranges as well, and so does boreal fire management. But nonetheless, the conclusion that if we were to sort of increase fire management resources to keep carbon in the ground, it could actually be a cost-effective way of doing so as we limit emissions in other sectors. So the basic conclusions from this research are, we know fire regimes are intensifying now. We expect them to keep intensifying. Those CO2 emissions, and I should note, of course, there are other emissions besides CO2, methane, NOx, things that affect ozone. But we just looked at CO2 because it's the one that's costed globally. So those could be notable on a global scale, could potentially impact our ability to meet global climate thresholds. We found fire management as currently practiced is effective at limiting fire size, and there's actually reasons to think it could be slightly more effective. How am I doing on time? Okay, all right, wrap up, okay. The cost of avoiding those are comparable to other mitigation technologies. There could be other benefits too, just in thinking in terms of, smoke impacts on society, habitat, other damages, increase in jobs, et cetera. And all the further research is required. We do think policymakers should strongly consider boreal fire management as a mitigation strategy. Okay, thank you.
It seems like historical fire suppression is often blamed for the sort of the huge fires that we have in the western lower 48.
Yeah.
So I'm just like, do you think, is that
Yeah.
really the answer?
Well, it's a
for
great
Alaska?
question. So, yeah, and it's a question that comes up a lot. So on the one hand, you have to very much realize that the fire regimes in the Western US are quite different than the ones here in Alaska and Canada. So, I mean, here they're mostly occurring in black spruce forests that are essentially as flammable as they're going to get. In the Western US, you typically have these high frequency, low intensity fire regimes that have been modified by fire suppression. So you have the buildup of these ladder fuels. So on the one hand, we don't have the same dynamics. We would also never sort of suggest suppressing fires below the historical levels, right, to influence on habitat and things like that. So I think, I think there's different dynamics at play. And the one thing to consider is that the younger forests are often less flammable. So even though if we suppress a fire today in a black spruce forest, it probably is not going to become more flammable. If it were to burn, it might become less flammable, but it's kind of an open question how much less flammable and how long that lasts. So the research that I know about says maybe that effects last to about 20 or 30 years. There's a paper by Young et al. A couple years ago showing that young forests burn about 6% less than they would be expected to otherwise. And I've seen some other stuff come out that the effect is actually relatively minor, especially in later season burning and large fire seasons. So yeah, I mean, it's a tricky issue. We would never sort of want to, we've realized that these are fire adapted systems. We're not trying to fundamentally alter the way that they work or anything like that, but fire regimes are intensifying and it's emitting lots of carbon. And if we can sort of even bring it down a little bit to cost effectively keep carbon in the ground, it seems like a decent idea.
We can take a really quick question.
Okay, there's one online question.
Yeah.
And I just want to say, management is not suppression. It's not equal. So
No, that's a good point. That's a good point.
Are you suggesting, Brandon, suppression or management for a specific low? Oh, that's not the one I was looking at. Jackie, you asked two questions. Does the analysis of the cost include implementing management because they're very remote locations? These are very
Yeah,
remote.
no, that's also a really good question. So, the next step is sort of like, how would one implement this? And those are big considerations. We did do a road analysis, so look at fires close to roads versus not, and the effectiveness did not change actually, which is interesting. One would expect, but yeah, it didn't show up in the data.
And Jackie has more questions for you later. if you
Jackie
can
Schumann? or-
Yes,
Okay,
it's asking questions, so you can.
good,
talk
all
to her
right. Well,
later.
You have a poster, right?
I do. I think it's tomorrow.
Same thing?
Yes.
Okay, yeah, we'll
yeah,
talk more
yeah.
about it, yeah. All right,
Yeah,
thank you so
thanks,
much.
everyone.
All right, next up we have Rebecca. Development of an Arctic boreal fire atlas using visible infrared imaging video emitters with active fire data.
You have a question?
Yes, so I'd like to present a product that we're currently developing together with Jim Rendison and Yang Chen from UCI, and we want to develop a circumpolar Arctic boreal fire atlas, which is going to be based on relatively high resolution US active fire data. So yeah, maybe first, why do we need a new fire atlas? So basically we want to get from this, so from point data on active fire detections to this, so really object-based fires, and then kind of see how they spread in a sub-daily scale. Because this really sub-daily information can then be linked to weather and geographic conditions and can tell us when and how intense spread events will happen. And we hope that this will also be useful then for example, for fire models. And there is currently some global fire atlases available. They are all based on MODIS burned area data, and that brings with it a couple of problems. One of them is that the ignition retrievers don't work very well in boreal regions, so we have a lot of really scattered ignitions, so it's not very useful. We also don't detect all the burnt areas, so small fires we don't detect, and also, for example, a previous study in Siberia showed that even in the large fires, we often miss about 40% of the total burnt area. So VIRS really helps detect this then. And MODIS burned area is only going up to 70 degrees north, but recently we've also seen a lot of Arctic fires that are further north than that, and we also want to really capture these. And then one last point that we really want to develop as well is circumpolar ignition attribution. So we want to check for each ignition, was it caused by lightning, by humans, or maybe even by overwintering fires. This is the basic algorithm, which is based on the Californian Fire Atlas, which was developed by Yang Chen. So that is currently in press with scientific data. Basically, it works in 3 steps. First of all, we do a unsupervised clustering of all active fire locations. So that is then these C1, C3, and C2, these clusters. And then we decide for each cluster, is it a new fire? So for example, the fire 3 up there, or does it belong to an existing fire, such as cluster 2 and cluster 3, and then we expand that existing fire. And then as a last step, we check whether 2 fires, so these fire 1 and fire 2, have grown together. And this is based on spatial and temporal distance. And we use land use data and also peat coverage to really tune these spatial and temporal distances. We have a set of outputs. First of all, sub-daily fire parameters. So here you can see the sub-daily parameters for a fire in the Northwest Territories. We also correct these for lakes using a high resolution lake data set so that the fires go neatly around the lakes and not through the lakes. We also output the fire line. So where is the fire currently active? And then we give summary outputs, so an annual layer of ignitions and also an annual layer of final parameters. We also output a set of parameters, so of course the start and the end date of each fire and the duration. Then for each time step, also the area of the fire, the perimeter length, the length of the fire line, so the active fire front, so to say, the number of new fire pixels, the pixel density. We also account for smoldering time, so when the satellite cannot detect the fire, and we report then the time a fire has been inactive. We also report fire radiative power, so how intensely the fire burns as seen from the satellite, and the fire type. So here you can see an example for that. This is an example for southern Siberia and Mongolia. You can see like here these cropland fires in pinkish, so they're really small fires, and then further north we have forest and shrubland fires. And lastly, we also output lake area and the number of lakes, and maybe also interestingly, the perimeter length that is impeded by lakes or surface water. Yeah, so currently we are developing this, and here you can see an example for the month of burning so this is good for 3 different years, and you can see in green and yellow the southern Siberian spring fires, and then in reddish colors the classical boreal summer fires. Here also see some fires in autumn. And we're finishing this up currently, and then we want to really get to the ignition source attribution. So having these, being able to say for each ignition whether it's caused by lightning or humans. And then we were going to get to some interesting science questions. So looking at contrasting fire behavior across continents or regional differences in the dominance of ignition sources. Also, we can, with this high resolution lake data set, we can look at lakes and wetlands as regulators of fire spread, and potentially also thinking about what is controlling unburned islands. Thanks.
How frequent are the VIRS acquisitions? You repeat that, it seems.
Yeah, so it depends on the latitude. It's at least twice daily. But if you go really far north, so to some tundra regions, we might be able to have even more overpasses, but it's maybe not enough yet to really have 4 daily overpasses, so that we can have like, yeah, even more than half daily time steps.
It's really nice.
Yeah.
I got a question.
Yeah.
So you use VIRS, and I assume they'll be affected by the constant cloud cover in areas like Alaska, right? How do you account for that?
Yeah, so what we do for our final perimeters, we also correct them using modus burned area to have like the best estimate. But most of the times it doesn't really change much. So since it has so many overpasses, it seems to capture the fires quite well.
Okay.
It is maybe a problem when looking at unburned islands, but for the perimeters, we really just take the outer area. So if there's, yeah, that makes it a bit less sensitive.
The MODIS data, they do underestimate burn area in Alaska. But we can talk about that later.
Yeah.
Thank you so much.
There's a question online from Chris Weigel. Who says, do you make use of the viewers on both the SNPP satellite and NOAA 20?
Yeah, that's a good question. So far we're only using SNPP because we're using the active fire location data, and that is not currently processed from NOAA 20. But we also want to look at if we can and how we can include this data. Because then maybe indeed it will be possible to increase our temporal resolution, which would be great.
Thank you. So next up we have me. Thank you. Yeah, so this presentation is about tundra fires in Alaska. First, I want to acknowledge my awesome co-authors, some of whom are here today. This paper, the results is in the second round of review at Nature Plants, but I've made it publicly available via preprint. So feel free to refer to the preprint for more details. And also, if you are reviewing this manuscript, please be kind. All right, so introduction. The Arctic region, as we all know, has experienced the highest level warming over the past decades. And one of the consequences of this potential warming is that there is a process called the greening process, which is kind of widespread. And there have been many studies that look into this, and the common consensus that shrubs play a major role in this. Also, fires are a major disturbance agent in the tundra, and they have known to promote the growth of shrubs. And because shrubs have more biomass, and they can sustain more severe fire than graminoids do. So this fire, shrubs, and fuel relationship has been speculated in a term called fire shrub positive feedback loop. And there have been several studies that shown that this positive feedback loop exists. But we didn't know whether this feedback loop widely exists across the Alaskan tundra, and that's why we look into this. So the study area of this study is Alaskan tundra. We divided into 4 regions: the North Slope, Noatak, Sewell Peninsula, and Southwest. Here you can see they pretty much account for all burn areas since the 1940s. I have more slides than I have time for, so I'm not going to go into details. But very quickly, we generated a lot of random sample points across the Alaskan tundra, including burn and unburn, and another type of point we call background points. And then we use those points to extract in the annual maximum NDVI based on the Landsat data hosted on the Google Earth engine. And then we extracted those values, and then we calculate the NDVI max anomalies, and then we generate trajectories. And then we did that for all different subsets of burn sample points based on different landscape types, physiognomic types, stuff like that, but also burn severity. We did field work. We visited the Sewell Peninsula and the Noatak region over 3 summers. We collected a very comprehensive suite of data. We visited more than 100 sites. We collected a whole bunch of parameters. Some of them are not related to shrubs, but some of them are. All right, so don't really have time for the detailed explanation of the results, but very quickly, this is the trajectories we generated for different burn severity levels in different subregions. Feel free to take a look at this and also the preprint for more details. We can talk more, offline. And this is a trajectory that's based on high severity burn only, but divided by physiognomic types. So you have graminal tundra, erect shrub tundra, and wetlands. They show very interesting patterns, very different patterns as well. And this graph is a chronal sequence we generated based on the field data we collected. This is about this is based on vegetation cover. And these are some correlation analysis we did based on the field data also. So let me jump into the conclusion. We have confirmed the wide existence of fire biomass positive feedback loop across Alaskan tundra. Notice here I use the term fire biomass positive feedback loop instead of fire shrub, because based on remote sensing data, there's no way for us to definitively separate shrubs from graminoids. But we do have evidence to show that at the landscape level, this feedback loop is dominated by shrubs. And also, high severity fires have substantially larger impacts on species composition and succession trajectories of tundra ecosystem than moderate and low severity fires. Considering future projections of increases in wildfire occurrence in the tundra, and also the extent of severity, tundra wildfires are likely to exert a stronger impact on tundra ecosystems, which means that the ongoing domain-wide stratification process may be further accelerated by wildfires. Now, our study shows that some tundra ecosystems are more resilient to wildfire than others. This means that despite the ongoing strong Arctic warming, the intensification of wildfire regimes, and the transformation of the dominant vegetation species may not be the inevitable future for all of the Arctic tundra. Collectively, we want to say there are still a lot of things we don't know about tundra fires. For example, we don't know well about the fire distribution outside Alaska, especially beyond, before 2000. And also, we have a lot of uncertainties about a lot of the ecological impacts of wildfires. So that's kind of like the main message of this paper is that we don't know a lot. And with that call for more field campaigns in burn sets in different tundra ecosystems, and maybe do some little bit, prescribed burning. I remember, last time with Fairbanks, like 5 years ago, I remember JJ said, let's burn some tundra. I really want to repeat that. Also, before I start, I want to do a shameless promotion of a special issue that me and my colleagues from the Modis and the Beers team, in remote sensing journal, this is about remote sensing applications, wildfire research and management. All right, so we would be greatly appreciated if we can consider submitting to this special issue. And if you do, please let me know, because we are able to give out 30% discount on publication fee. So yeah. All right, thanks so much.
Any questions for?
First time. I mentioned this yesterday, but Matt McKander has recently developed these plant functional type maps from 1985 to 2020 across all of Alaska and Yukon. Would be really interesting. The data sets are available on the DAC papers just out, in final form yesterday. It might be interesting to see how that supports your findings or not.
Yeah, definitely. Actually, use his data for this manuscript. Yeah, but I'll be talking to him about it. Great, thank you for letting me know. All right, thank you so much. Okay, is there anything to chat? No.
I didn't see.
All right, next up we have Laura. Is Laura?
She is online.
Yes.
All right, Laura's presentation is called Understanding the Interactions between Wildfire Disturbance, Landscape Ecology, and Post-Fire Recovery in Real Taiga Ecosystem.
Laura, do you want to share yourself or shall I share?
I can share if you want me to. Let's see.
Thanks from Laura.
No, I think it's from Laura. Okay. She's at the airport waiting to get on her airplane.
Hopefully I will be there tomorrow. So.
Yes, that's good.
Okay. So I'm presenting today on our TE project from phase 2, understanding the interactions between wildfire disturbance, landscape hydrology, and post-fire recovery. And it's focused primarily on the Great Slave Lake, boreal taiga ecosystems. And I'm focused today on modeling only because of the short presentation. And these slides were largely put together by Jackie Schumann, who's a co-I at NCAR. We also have a co-I at UMass, Paul Sakara, and then here I've listed our contributing authors from UMass, and Sean Swenson and Adriana Foster are also part of NCAR putting together these slides that I've been going to be presenting. And then we have collaborators, mainly in this talk from CFS. So I wanted to start by talking about this paper that Jackie has in review for PNAS Nexus. This is based on an NSF workshop with 92 fire experts. And this paper is really focused on re-envisioning fire science, both for modeling and just in general research, just to look at integrating across disciplines, co-production of knowledge, coupling it with human dimensions. So rather than being in these just small silos of a couple of these factors, just really to work together and answer fundamental questions and be able to look at applications and specific applications, especially with the increase in fire regimes that are occurring not only in our above study area, but globally. So the modeling that Jackie's been doing has been parameterizing or benchmarking. I mix up which terms I should actually be using. So I'm not a modeler, but she's been using FATES, and it simulates plant physiology, competition processes, ecosystem assembly, vegetation distribution, and she's been parameterizing it for the boreal and Arctic region. Previously, it had not been, as well as integrating it with the hydrology and the fire models. So this is just showing how she's been doing some site level testing along with Adriana Foster, comparing UVA FME to FATES, trying to make sure that they're getting the outputs correct as far as stand age and biomass that's occurring by species. And they've used our field data as well as UVA FME data or model in order to do this work. So this slide shows some of the products that we've been developing from remote sensing, in addition to the field data that we've collected, both for the modeling, but also to train and validate these remote sensing products. And so some of the early ones you've probably seen before, we have burn severity, and that's focused on the ground layer. So looking at the moss and organic soils and not the canopy. So that's kind of important, especially for the peatland ecosystems, which we've been focused on. We also have the ecosystem type maps, and these are both available on the DAC. Some of the more recent products from UAVSAR, the L-band soil moisture retrieval maps we've been producing, and those have pretty high accuracy. I think that one's like R² of 0.85. And then the C-band drainage maps from a time series of C-band data over the burn scars. We've been working on L-band to get that to work for the non-burned areas. And then Paul Sakura and Simon Kratz worked on L-band biomass maps, both from UAVSAR and PulsAR2. So we also have been analyzing the effects of fires, 136 fires using some of these data sets, but I don't have time to present on that. I think it's going to be presented in R2O. So the hill slope hydrology model that Sean Swenson largely leads replaces traditional single column flow with multiple connected columns. And one of the problems that he came across for our study area, especially in the Taiga Plains, is that there's not a whole lot of range in elevation. And so that was kind of limiting how he was benchmarking it. And so he's been using as a proxy the ecotype and soil drainage maps that we've produced. And that is shown here. And then in this next, showing the output by using the land cover, which obviously fens and wetlands are going to be at lower elevations and wetter systems than the upland. And so he's got these outputs showing that it's capturing seasonal surface water changes from spring and then late summer. So the next steps for the modeling are to test the active crown fire component, confirming the vegetation allometry even further that from the field and comparing with UV FME, implementing a dynamic moss layer, which is pretty important for this region, simulations with initialized inventory, active fire, and variable drainage. And then we've also been, and we'll do some more comparing campfire outputs of fire effects to what the models show. I think that's my last slide.
Any questions?
Laura may be here tomorrow.
Maybe.
I'm hoping to be there tomorrow. I'm on standby for a flight
There's something.
at 6 o'clock.
A question, Randy?
Well, it's from Jackie, actually. Jackie's online and she says, pleased to report that the active crown fire is functional and will be doing for the testing.
Okay. Thank you for mentioning that.
All right, thank you so much, Laura. Next up, we have Allison. Emergency Department Visits and Wildfire Mission Alaska 2014 and 2019.
Promise to be quick so we can go to lunch on time. So thank you, everyone. So this is the effort from above phase 2. So this is a little bit of work that's also co-eyed by Tony, Nancy, Tatiana Laboda, and Robin Hewitt. And also the data set that we'll be using and talking about here is from the Alaska Division of Public Health, from their health facilities data and reporting program. So as we all are probably aware, speaking sort of to the safety already, PM 2.5 is emitted from wildfires, and just looking at this graph from 2001 to 2019, there's a lot of emissions that occur every year, specifically looking at the Arctic boreal region. And so with that, PM 2.5 is noted as such from the size. It's particulate matter that's less than 2.5 microns, an aeronomic diameter, which means that it's really small. There's even evidence from the epidemiological literature that it is so small that it can actually seep through your skin. So there's very little protection sometimes for you to not have it sort of infiltrate deep into your lungs, deep into even sort of like the blood-brain barrier. So you can see an assortment of literature here that looks at a lot of different health outcomes, and also sort of that wildfire specific particulate matter and sort of assessing those relationships. And the literature is growing, specifically looking at cardio outcomes and also those respiratory outcomes, which are a bit more intuitive. And so what we have been looking at with that data set for the Alaska inpatient and outpatient emergency department visits, specifically looking at the emergency department encounters for outpatient, is taking a first cut look to see what circulatory, so that's sort of like your cardiovascular events, heart attack, strokes, and also respiratory encounters, so like our asthma, COPD, and what relationship they have with fire. So here is a figure looking at specifically just 2015 to 2019 on top. This is from the data set that Tony has created with continuous PM 2.5 measurements. And we chose 2015 and 2019 with sort of the realities of data for the hospitalization data set. That is sort of just the best quality data. We would have loved to have sort of data from the 2004 season when there was just the record PM 2.5, but limitations for wanting to use the best available data. But as you can see up here, there is a pretty big disparate difference in the seasonal PM 2.5. So we fortunately have like a bit of good years. And so what's interesting here from like these two items here is that for July, typically we think about the fire season. It's usually when most of the fires do occur, but the respiratory encounters seem to be fewer there. So it's an interesting hypothesis for us to explore as to why might that be the case. There is some research that suggests that people just aren't prepared for those earlier fires maybe. And then by the time that the fire season comes, you have acclimated appropriately. And so we can see differences in circulatory sort of cardiovascular events as well. So here, just looking at by region, the different types of encounters for people who went for their first or second diagnosis code. As we could see, probably unsurprisingly, Anchorage sort of has the most in here. And then I will put in a plug for the poster tomorrow. And what I haven't talked about here and what I can talk about later in the poster session is we have a parallel effort with the Alaska Center for Disease Control Prevention, the CDC, looking at similar epidemiological trends with the exposure data set with the PM 2.5 for 2001 to 2019. And we're encountering a lot of really interesting challenges with applying epi models to Alaska, because epi models are generally constructed in those methods for larger, densely populated areas. So trying to apply those methods that are really constructed and built for urban populations to a state like Alaska that has a lower population is a really interesting challenge and a really great opportunity for storytelling. So I'm really happy to talk about that later. Thank you.
Is there another question? Because mine's not a question.
Yeah, I'm just curious, so Fairbanks, boreal forest, fires are big here, not so much so in Anchorage. So I'm wondering, gosh, is it just the population size in Anchorage so much greater and that's why there's so much more exposure? It's okay.
Yeah, that's a great question. Yeah, so that's something that we're definitely going to look at, specifically looking at sort of like the actual pattern of emissions. I think Tony's going to present on that at the workshop, which will be there. So like where the fires occur is not necessarily where the smoke goes. So that's also something that we're playing.
Anchorage actually has a much better air quality than Fairbanks. I guess it's being blocked, like emissions blocked by the Alaska range. So actually, yeah, it's much better there. And I guess that's one of the reasons why.
And you looked at cost data from 2019, right? That was the Swan Lake fire close to Anchorage. So that's going to have an impact.
Yeah, because the numbers there are cumulative over the season. So what we can also look at is like the difference by year.
Yeah.
So it could be biased towards that.
Yeah, we can estimate PM2.5 for the entire state of Alaska for every day. So and they're all fire related emissions.
Okay, and so that was if I can have a follow-up question. So you're estimating the exposure to P 2.5, so based on fires, because
That's
obviously there's
fire
other
related.
things, that contribute to it. So yeah, okay.
Yeah, that's his area.
But mostly because a lot of rural areas, people living in rural areas, and they're now affected by like anthropogenic emissions.
Yeah.
They are affected by wildfire probably more than the anthropogenic sources, and that's why our product can help, because we can actually see, how many people are affected like outside the cities. But the other thing is a lot of areas outside the city, they don't have air monitoring station. So being able to know how much PM2.5 they have on every day, and it's going to be helpful. At least that's a thought.
So I just, I know we have one more. This is a time to say that Allison was a part of an effort that Tatiana Loboda and myself and Robin Pewitt, who is a co-investigator in this project. We're putting together a book on fire, smoke, and health. It's not for boreal specifically. It's an AGU publication. It'll be coming out hopefully by the end of the year. And Allison wrote one of the chapters. So, yep. So look for the book so you can learn more about that.
All right, thank you, Allison. All right, last but not least, we have Sander. Fire in the land of ice, climatic drivers and feedbacks, and the ERC project affiliated with the above. Go ahead, Sander.
Hi, everyone. I'm going to take the liberty to take you out of the above domain for a little bit and towards Siberia. And this magnificent satellite image from Veers was taken in June 2020 over eastern Siberia. See that the sea ice in the Arctic Ocean is still breaking up, and see all the smoke and the fire scars that are ongoing. And this is well within the Arctic Circle, so this is very, very far north. So yeah, I'm Sander van Averbeek, if you Amsterdam, and I just want to kind of introduce a new project that we started a few months ago in Amsterdam. So titled Fire Ice, Fire in the Lands of Ice, Climatic Drivers and Feedbacks. It's funded by the European Research Council, but we are very happy to be affiliated with NASA above, as that allows us to keep in touch with all the great stuff that is happening here. And so also sincere thank you for having us here. The names that you see listed here, co-authors, is they represent the Fire Ice team. So in this graph, you see the cumulative number of MODIS active fire detections over eastern Siberia for each year within the MODIS record. And so you really see that the last 3 years, so 2019, 2020, and 2021, over eastern Siberia, and these large forests, which represent around 20% of the boreal forests, they really stand out compared to the rest of the record from MODIS 2001 to 2018. And obviously, this was a huge motivation for my project. And I mean, there's several questions that, if you see this, it's like, why is this? What is really going on? What are the climatic drivers behind these recent extremes? And then also, what is the impact? So, what is the impact on the carbon storage of these forest and tundra ecosystems? And also, what is the impact on the permafrost? So these are really some of the driving motivations for the Fire Ice project. The project will run until 2026, which I believe is more or less the end of the whole above program as well. So we do have a focus on Siberia, at least that was our intent when we wrote the proposal, especially for the field work. I mean, it's a little bit problematic now with the ongoing situation, so we'll have to see what to do about that. But what I wanted to say is that with the remote sensing and the geospatial analysis, we basically have a pan-Arctic focus, which then also includes the above domain. I'm not going to go in detail about parts of the science question, but it's just a large overview. So the overarching goal of the project is to unravel relationships between climate, fire, and carbon in the boreal and the Arctic. And for that, we have a couple of work packages that will look at the carbon side. So some of the driving questions are, what are the emissions from these fires? Are these flaming fires? Are they smoldering fires? What are the consequences for CO2, methane, CO emissions? Very important part of the project focuses on the interaction between fire and ice, permafrost. So does the permafrost degrade after a fire? Does that happen in an abrupt way? Is it more gradual? Or maybe it just recovers? What are then the consequences for potential additional emissions of CO2 and methane from fire-induced permafrost stop? So that's more on the carbon side. Then we also have work packages that are more focused on the fire extent, the burn area. So what makes that fires grow, and maybe also importantly, what makes them stop? What are the limits to the growth of these fires? Is that changes in fire weather, or is it more like bottom up, like landscape controls on the growth? What are the controls on ignitions? Is it people? Is it lightning? Or is it maybe overwintering zombie fires? And how will this all change in the future? So those are really a lot of questions that I put out here, and hopefully also some answers a couple of years down the road. So we haven't really had the opportunity to go out in the field with my team in the last few years because of COVID. So this is a picture of our team between two lockdowns playing petanque. I don't know how you translate that in English, jeu de boule or something like that. Playing with a ball. But so that's our team in Amsterdam. We work together with Woodwell, Brandon as well, Northern Arizona University, Michelle Mack and Sante Walker, and hopefully also our Russian collaborators, which I'm for the moment not allowed to put on the slide here. Yeah, that's it. Thank you. Happy to answer any questions.
Question?
Senator, how far south are you gonna go in terms of a domain?
Yeah, so for the field work, our initial plan was to kind of cover a whole gradient from southern Yakutia, so that's around 55, 56 degrees north, and do like a sampling campaign there up to within the tundra, so up to like 70 degrees north. That was for the field work, but I mean, that's a little bit hanging for the moment. Yeah, I mean, otherwise the domain is really the entire boreal forest and the tundra for the remote sensing analysis. So yeah, pretty far south, I would say.
Great.
All right. Any other question? All right, if not, I wanna thank you to all the presenters. I'm sure there will be a lot of interesting conversations offline about this awesome work. All right, thank you so much.
Before people break, there's a bunch of handouts from AFSC up at the front, stickers and some reprints and things like that, so help yourself.
Here.
Thank you. Very good job.